Hi, I'm Dr. Detail. Welcome to my laboratory. I'm in a light-polluted part of the universe. I've been creating a secret. It's a filter that lets only in hydrogen alpha light. Let's take a look at what it can do. You'll be amazed. What? Everything is darker? My signal is cut in half? Excellent. That's exactly what I was hoping for. Welcome to Deep Sky Detail. Have you ever wondered why filters work? I mean, you probably know the basics. The light entering your telescope is a mix of the DSO and light pollution. The filter gets rid of the light pollution, allowing the pure signal of the DSO to shine through. You're basically increasing the signal of the target. Okay, but that explanation is not exactly correct. And how much better is a light pollution filter than no filter? And why is a stacked image from a light pollution filter so much darker than a broadband image? Like, I have to stretch a narrowband stack a lot more in software to make things bright. Why is that? In this video, we'll quantify exactly how much better a relatively cheap HA filter is on an HA target than just a luminance filter. We'll examine exactly how a signal changes as you stack in a more or less scientifically valid way, not just visually inspecting things. Let's do some testing. Okay, let's go over the characters. I'll be using Orion Steel, my doublet 80mm refractor from Orion for this test. He may have a small aperture, but with a 0.8x reducer at f6, he is also not very fast. Steel will be riding his trusty steed, Mountie Sirius. Together with their lookout, Cassiopeia Ray, a ZWO-294 Pro camera in bin 2x2 mode, they'll measure the Flaming Star Nebula, or IC405. Cassiopeia works with her sister, Stella Guide, a ZWO-224MC, an off-axis guider to keep everyone in line. The comparison will be between my Optolong 1¼ inch L filter and Optolong 1¼ inch HA filter with a pretty big 12nm bandpass. The bandpass determines how good the filter is, and good HA filters have a bandpass around 3nm. So mine is pretty cheap, to be honest. But we'll see how it performs anyway. Let's decide how we'll take the pictures. I think we'll take around 1520-second luminance images, and then a 1520-second HA images right after another. Sounds good, right?
No! No! No!
There is a huge problem doing it that way. If I start early in the evening, the luminance images would be low in the sky. The HA images will be higher, going through less atmosphere. There's only one way to do it. What do you think, Stella? You're right. We'll have to take a 120-second image in the L filter, switch filters, refocus, and then take an HA image. We'll keep switching and refocusing each time. It's tedious, but it needs to be done. This is scientific-esque, after all. Alright, so how are we going to measure signal? In a previous video, I measured the signal to noise ratio of Messier 101. It goes into detail as to how I got accurate signal and noise measurements. To sum it up here though, I'll take a sample of pixels of the part of the nebula I'm interested in and get their brightness, and then take a sample of the sky background brightness. For each sub, I'll get the brightness of each pixel in the nebula and subtract the average sky background brightness from it. I'll then take the next registered subframe and do the same thing. It's also the approach I used in this video, meaning I'm treating the signal as the average brightness of the nebula, not the cumulative sum like in this video. I know it's controversial, but the two approaches are basically the same thing, as proven in this video. For each image, I'll have a brightness value for a sample of the nebula. In other words, I get the signal for a part of the nebula. Nice. I can then take the cumulative average of the signal to see how stacking affects the signal. At this point, I should confess something. The night I did this experiment, my mount was acting up. I've since re-greased it and it's working much better, but that night I had to throw out about 1/3 of my subs. Luckily, because I was alternating between HA and L, I threw out roughly an equal number of subs for both. So I ended up with 10 usable HA frames and 12 usable L frames. Let's go ahead and pick part of the nebula that we want to sample. Let's cheat a bit and look at the stacked luminance and HA images. When we find a suitable sample, we can work back in reverse to do our calculations. Okay, now to find a brighter part of the nebula that doesn't have any stars. We'll just pan around here until, nice, this part looks pretty good. I'll write down the coordinates of the corners of the box. Now I just have to find a suitable measurement for the sky background. Time to go through each sub one by one and get thousands of brightness values for the background and sample images. It's going to be so tedious. Oh wait, I'm bad at coding in R. Bad code is usually better than manual data entry any day of the week. Much better. Let's use bad code. Okay, opening R, putting in the numbers, letting it run, and voila! Oh wow, look at this graph. On the y-axis is the signal, and the x-axis is the number of subs that are stacked. The signal in H-alpha is around 200 ADU, but in luminance it's around 800. The signal is 4 times better in luminance than HA? What is going on? Something must not be right. What the I mean, look at this stacked HA image of about 20 minutes. Now look at this stacked luminance image of 24 minutes. There is much more detail in the HA image with less exposure time. How is there less signal? We even subtracted the background brightness from the nebula sample, so it can't be the increased light pollution. The filter really is getting us less signal. Okay, calm down. Maybe it's just the brighter stars. Yeah, the stars make it seem worse. Let's remove them. Oh, nope. Everything is still darker in the HA image, but it looks so much better, more crisp. What is going on? Is my filter horrible? But it can't be horrible. It looks better in HA. Stella! Stella, guide me, please!
Hey, Stella!
What's that? Oh yeah, the answer is clear. It's pretty obvious. Let's look at the noise. How should we measure that? It's again explained in my previous video, but to sum up, basically I'm taking the standard deviation of the sample as I stack, and then take the cumulative standard deviation of the standard deviations. It's a bit complicated, but it is the best way to do it. See that previous video for an explanation. And here it is. The noise in the H-alpha image decreases from about 6 to 5 as we stack the 10 images. Let's zoom in a bit. You can clearly see that the noise is decreasing. Nice. But the noise in the luminance goes from about 63 to 57. It's 10 times bigger. So if we take a ratio of the signal and the noise, or the signal to noise ratio, or SNR, we see that for H-alpha, the SNR increases quite rapidly to 42 with only 10 stacked subs. But in luminance, it is around 14 at 10 stacked subs. H-alpha's SNR is 3 times better. Nice. SNR truly is the queen of astrophotography. There is nothing more important than her. But you might be asking yourself, hey, Dr. Detail, what about faint areas of the nebula? How much better are those than the bright areas? Well, let's find out. Let me do the same thing with a fainter area. Alright, so the luminance shows the same pattern. It has more signal than HA, makes sense. And the noise is also much greater for luminance. The SNR then is about 10 times better for the HA filter than the luminance this time. Wow. So you might be asking yourself, why is that? Why are faint areas more affected than brighter areas by light pollution and sky glow? Well, to give you a hint, let's take a look at the distribution of photons hitting the sensor from light pollution. And subscribe to find out the answer in a future video. Thanks for watching.